Welcome back to My Smart Learning. This is a lesson for Year 12s, so it's A-level biology, and it's going to be on transpiration. So before we start, Joe's the one that thinks he's the funniest in the class because he's always, cracking out with his jokes and stuff, and everyone's always having a go at my jokes. So I thought we'd start to see how good our jokes are. Well, we'll test out, compare it to Alexa, see if Alexa's any better at these jokes. Alexa, what's the joke of the day?
What does a vampire use as payment? Cryptocurrency.
And you think mine are bad, right? Okay, I'll give it a rest now. So, what we're focusing on today, transpiration. So this is in chapter 7. We're coming towards the end of it. We've been looking at the circulatory system, and we looked at heart disease. Our learning objective today is how and why does water transport through plants? So how and why does water transport through plants? How does it happen and why is it important? Quick recall PT, our recall quiz, our high five. Make sure you get all 5 right and you'll get a virtual high five from me. People have been asking, so online, so keep asking. Question 1. What do we call the relationship between two sets of data? What do we call the relationship between two sets of data? Question 2. What do we call the link between two sets of data? So if there's a link, if there's evidence and there's a link between two sets of data, what do we call that? Question 3. How would I get valid data for epidemiological studies? How would I get, what 2 things should I do, make sure my data is, so that I get valid data? Question 4 even, what are the 2 main factors from smoking that causes coronary heart disease, CHD? What are the 2 main things in cigarette smoke that are the main contributors to coronary heart disease? So this is back from our previous lesson. Obviously there's multiple things from smoking, but the 2 main things that I spoke about last time. And question 5, what are the 2 main factors from diet that sort of contribute to CHD, coronary heart disease? If you want to press pause, just check your answers, give yourself some time to make sure you got the answers to that, and we'll go through the answers now. So the relationship between 2 sets of data is known as a correlation. So a correlation, so we can have a positive or we can have a negative correlation. If you've got evidence that links those 2, because remember there could be a correlation, but that does not necessarily mean that's caused it. So if you get evidence to show the link, that's a causal link. So that's a keyword there, link, causal. So a causal link. Question 3, to get valid data then, you need to make sure that your data is a large enough sample size. So you need to not rather than just ask 2 people, you've got thousands of people that you've asked or collected data from, and you need it over a prolonged period of time. You can't just have it over a couple of days or a week or so. You need it over a long period of time. And 2 main factors from smoking, we looked at carbon monoxide and we looked at nicotine. Okay, so carbon monoxide and nicotine are the 2 major factors. You've also got obviously tar from cigarette smoke as well, but it's the carbon monoxide and nicotine that we focused on last time. And question 5, the 2 main factors in your diet. Remember, in an exam you can't just say diet or poor diet. You need to be a lot more specific in your language. So you need to say it's high levels of cholesterol, and in particular it's the LDLs that cause the problem, the low density lipoproteins, and it's also salt, which increases blood pressure, and that's what leads to the problems with coronary heart disease. So what we're focusing on today then is transpiration. It's a fairly tricky one. So some more learning objectives. What we're focusing on, how does water, the absorption of water and minerals through the root hair cells. So the first stage of it. We're looking very briefly at the structure of the root and the stem. We're looking at the structure and functions of the xylem and the phloem. Something called the apoplastic and the symplastic movement of water, the two major pathways. And the role of root pressure and the cohesion tension theory of how water moves through the xylem. Now, root pressure, they've actually taken that out of your syllabus. If you were studying this about 5 years back, you would have had to know about root pressure. However, it's useful to know about root pressure because you need to know how that water actually gets into the xylem in the stem in the first place. So it's worth knowing that at the beginning of the story. Transpiration and factors affecting the rate. Now we're going to move on to that in my next lesson. I've split this lesson, the transpiration lesson, if you're looking in your textbook, I've actually split it into 2 parts. So we're focusing on the transpiration theory today. Tomorrow's lesson I'm going to look at the transpiration, the factors affecting the rate of transpiration. Now we have done that a few lessons back when we did it in chapter 6, but it actually links better with this particular area. And then the last lesson of this week we're going to look at translocation. So we're going to also look at the adaptations of xerophytes in tomorrow's lesson. So why do we need transport systems? Well, what's the point of these transport systems? You need these transport systems because you need to move substances around the plant. We need to move sugars and we need to move water. Now, what we're focusing on today is transpiration. Transpiration is the movement of water through the roots, up the stem, and out of those leaves. That's what transpiration is. When we look at the sugars, which we'll look at in the next couple of lessons, so that's translocation. So what is transpiration? It's the movement of the water, and it's what we call a necessary evil. The sugars can move up or down, okay, and that happens through the phloem. But I'm not going to focus on that today. We'll just focus purely on the water. So why do plants need water? Well, the obvious answer is, well, plants need water for photosynthesis. So what's the word equation or the symbol equation for photosynthesis? Well, photosynthesis is carbon dioxide plus water with the arrow, with sunlight and chlorophyll, molecules found in chloroplasts, give you glucose plus oxygen. And if you wanted to do the balance symbol equation, it will be 6 CO2s plus 6 H2O with the arrow with light energy and chlorophyll, gives you C6H12O6 plus 6 oxygen molecules, 6 O2s. How do you remember it? Well, lots of 6's going there. I call it the devil's equation, 666. All right, so there are your big numbers at the front. Now, what is water needed for? Well, we need it for photosynthesis, and we also need it as a cooling effect, because if you imagine this plant is sitting in a tropical rainforest, really, really hot, if the temperature gets too high, enzymes will denature. Water has a cooling effect. So water, as it rises through, transfers that heat energy, so it doesn't heat up in one place. So it has a cooling effect because the water will evaporate from those leaves. So also, again, the water vapor takes away. It'll have a cooling effect on the plant. The leaves need the water for photosynthesis. The leaves also need to, the vacuoles will fill up with water because the cell sap will have water. It will make the leaves turgid. And if the leaves are turgid, they can face the sunlight and absorb as much light for photosynthesis. So what else do the leaves need water for? Well, the water is a universal solvent. It dissolves lots of stuff. So it dissolves lots of minerals. Well, how the minerals will get to there? Well, it needs to be dissolved in the water, and the water will rise through the plant. So water is essential for life. So that's why plants need the water. But a few minutes ago, I just said it's a necessary evil. Now, what do I mean by necessary evil? What does that phrase actually mean? Well, it means a bad thing needs to happen for a good thing to happen. So necessary, so it has to happen, it's necessary. If the plant gets no water, it's going to die. But it's an evil. So what do I mean by evil? Well, the plant, to get water to the leaves, it has to defy gravity, because water is, when it rains, obviously, or you water your plants, the water is in the soil, and the water has to be absorbed by the roots and go up the stem and to the leaves. It has to go against the laws of gravity. Water is extremely dense, so 1 gram per centimeter cubed, or 1 kilogram per decimeter cubed, which is 1 kilogram per litre. So a litre of water weighs a kilogram. So if you got, you know what it's carrying shopping, and carrying anything that's a liquid in bottles, it gets really heavy. Water is extremely dense. So trying to push water up is very, very difficult. If you imagine you're a fireman or a fire person, obviously, you've got your hose pipe and you've got a burning building, trying to get water really, really high up to get onto the roof, or high-rise building, it's very difficult. It takes an extreme amount of power and energy to get that water against gravity. It needs to gain lots of gravitational potential energy. So it requires lots and lots of force. Now, if you try to push that water up, it'll be impossible. Now, imagine some trees. Now, if you're a tree that's that small or a little bush, then that's fine. But if you're a huge tree that could be, tens of meters high, trying to get that water up there is going to be extremely difficult. So it does that by a process of evaporation. So the water has to evaporate through those leaves. So water needs to be drawn up, and because once it gets up there, most of that water, probably about 95% or more of that water, evaporates and leaves the plant. So why is it a necessary evil? It's losing most of that water. So if you got 100% of water going up there, and most of that 100% is gone, 95% or more of that water is evaporating and going, that means you've only got 5% of water. Well, that's a complete waste. That's like me giving you £100. I can see big smiles on your face. I'm not going to actually give you £100, but if I was going to give you £100, right, you'd be really, really happy. But if I said to you, I'm going to give you £100, but you can only keep £5 of it, you're going to have to burn the rest, the £95, that'd make you really sad. So you're left with a fiver. However, if you change your mindset to, well, have your mind of sort of a half glass full person or the glass half empty person, then you think, well, actually, I didn't have anything in the first place, but I've got a fiver. So a fiver is better than nothing. And that's the same thing that's happening with this. This plant is getting 5% of that water that's come up. The other 95% gone. It's evaporated into the atmosphere. But at least it's got 5%. At least it's got something that it can survive off. It's £5 is better than no pounds, right? So you rather have £5 than £0. So same thing here. These leaves will get 5% of the water, but the 95% is gone. That's why we say that phrase. It's a necessary evil. It's necessary, not a good thing that 95% is gone, but it needs to. So how does it happen? So I start off with this whole evaporation bit. Now the evaporation bit is really important because as the water evaporates out of the leaves, it causes a negative pressure that causes a pulling up effect, okay? And that will draw the water up the stem and into these leaves for the water to evaporate. But the story starts, rather than starting from the top here, I'm going to start with the story from where the water actually is. So the water is actually in the soil and it needs to be absorbed into the roots. So how does that start then? So what is the purpose of the roots? The roots are obviously down there. The roots, if you look at the structure, they have little tiny root hairs. Now the root hairs gives you a larger surface area to volume ratio because they're long and thin, and also they're very, very thin. So the diffusion pathway is going to be extremely small. So if we relate that back to Fick's law again, remember surface area times concentration gradient divided by the length of diffusion pathway. That's the rate of diffusion. So you want that to be maximized. So how does the water get from the soil and into the roots? Now, this is the thing. Water will move passively. You can't pump water. Water has to move passively. And that will happen via osmosis. So osmosis then. I need water to move from a high water potential to a low water potential across a partially permeable membrane. That's your definition of osmosis. That's what's happening. But how can I make sure that that system is in place? So how do the roots make sure that happens? How do the plants make sure that happens? Well, the plants have to actively transport mineral ions, like sodium and potassium. So they have to pump ions into the root hair cells. And by doing that, it makes it very, very salty on the inside and less so on the outside in the soil. And if it does that, then it means your water potential is very low inside the root, but it's very high outside the root. So water will move in passively along the water potential gradient. So that required energy. It requires ATP, okay? And cracking my old joke again with money jokes. I don't mean 20p short of a pound. Get that? ATP? No. All right, okay. ATP, adenosine triphosphate. It requires energy to pump minerals in, and water will follow suit. It'll go from a high water potential to a low water potential. So if you use a weed killer that's a metabolic inhibitor. It stops metabolism. If it's inhibiting metabolism, it's going to inhibit ATP being produced. And if there's no ATP being produced, therefore there's no energy. Therefore, there's no sodium ions being pumped in. Therefore, you're not making this water potential gradient. Water's not going to move in. The plant dies from dehydration. There's no water going in. It dries out and dies. Okay, and that's a very common sort of type of weed killer. So that's how water moves in. So we just mentioned the absorption of water. It will go through. Water enters via osmosis. Okay, because you've got a high water potential on the outside and a low water potential on the inside, because you've actively transported mineral ions into the root. Okay, so it's got in. Now I am going to post this on for my year 12 class. I'm going to post this on Show My Homework, so you'll get this PowerPoint so you can make your notes on there, and there's going to be a few little exam questions, some exam questions at the end of this. So once it's in there, then what happens next? So here you go, that's the soil particles there. You've got the water on the outside, you've got the root hair cell. Water will move into the root hair cells. But now it's into that root hair cell. How does it get into the stem? How does it get into the middle? Well, we need to look at the structure of the roots. So that's just on one edge of the root. So if I get a root, so roots like this for instance, and if I imagine I point it that way and I cut it across that way, that's called a cross-sectional area. So I'm going to take a cut through my root, it's pointing at you that way, and you can see this is a cross-section. Okay, now that is the cross-section there, but once you get into the stem, it starts to look more like that. So this is a cross-section of the stem, this is a cross-section of the root, and the main thing you should notice, you've got the root hairs on the outside and you've got the epidermis. Okay, epi meaning outer, dermis meaning like a skin, and then on the inner layer you've got another lining there called the endodermis. There you go, the endodermis. Endo meaning inner. So epi meaning outer, endo meaning inner, dermis, skin. Now this bit here, this pinkish bit here, it's not actually pink, but just for graphics sake, that is called the cortex. So from the root hair cells, it has to go through the cortex, and then it needs to get past this epidermis. And then once it's past the epidermis, then it can get into the xylem vessels, which is like an X, big X shape in the middle of the root. Your phloem vessels are sort of on these four quadrants, these four corner bits, okay? But the xylem are in the middle. So how do I get to the X? X marks the spot. That's where I want water to get into. Well, the water has to keep flowing in a forward motion, and it needs to get to this epidermis. And once it gets to the epidermis, it sort of hits a bit of a snag, but we'll get to that in a second. So what route does it take? Well, all this cortex, the water needs to keep moving in a forward direction. How? Well, this is our cross sections or transverse sections, longitudinal sections, because it's going up. So these are your phloem and your xylem. Your xylem look like this. They're hollow tubes. Water will only move up them in one direction, in one movement. And the outer walls are thickened and stiffened with a chemical called lignin. Xylem are technically, these cells are dead. So the cells on the outside of these xylem are dead, and it's lignin that strengthens them. Whereas phloem are made from living cells. Okay, and we'll look at phloem in more detail when we look at translocation. Now, so there's the lignin. It's kind of like spiraled around. So you've got live bits and dead bits. It's like hollow hexagonal tubes. So there's your xylem. Like we're saying, yep. Hollow dead tubes, and the water and minerals are transported only in the upward direction, and it's made of lignin. And they're very strong to support the plant. Okay, that gives you that sort of rigidity, strength. Phloem we'll look at in more detail next time, but it's to transport sugars, and it's made from living cells. We've got these things called companion cells, and we've got these little sieve plates, these sieve tubes that you can see there. Okay, now this is the bit I was trying to get to. So this bit is the cortex. So the cortex is that pinkish bit that I had on my root diagram from before, and it needs to get towards the epidermis. And there's two routes the water can take. Now these cells are side by side, obviously, and the water can either move through, don't know what's happened there, I think I've touched the wire, right, it can either move directly through the cell wall. Now remember, the cell wall is kind of like a mesh. So it's like a mesh like this. It's not like a solid structure. It's kind of a intertwined cellulose molecules. And because you've got little sort of tiny holes, water can, like, it's like a sponge or cardboard. It can sort of blotch its way through. So it can just keep moving forward. So this is known as the cell wall pathway. The cell wall pathway. However, in your textbook it says the cell wall pathway, and it's, for some reason, for the last 2-3 years, we've been calling it the cell wall pathway. It's always been known as the apoplastic pathway. The apoplastic pathway. And I keep teaching it as the apoplastic pathway because that's the way we were all taught it. And for some reason, the exam board, I don't know why, they've sort of dumbed it down and made it more simple, calling it the cell wall pathway. But all your science teachers, most people will always call it the apoplastic pathway. Okay? But it's basically keeps going along the cell wall until it gets to the middle bit, the middle ring, which is the epidermis. Now the other pathway is through the cytoplasm. And so it goes through the cytoplasm from one cell to the next. But you'll think, wait a second, how can it jump from one cytoplasm into the next cytoplasm of the next cell? Well, it can't just jump across because the cell wall's in the way. However, these special cells in the cortex have a little pathway. It's a little bit like this room is connected to the hallway, then the hallway is connected to the kitchen and the dining room, whatever, right? So there's doorways. There's little pathways or doorways between these cells that sort of open, and they stay open. And these little pathways where the cytoplasm of one cell is mixing with the cytoplasm of that cell is called a plasmodesma. Plasmodesma. So plasmodesma is one of these little pathways the cytoplasm meets. Because there's multiple of them in multiple cells, we call it plasmodesmata. Plasmodesmata. It's a bit like stoma for one hole, and stomata, plural, for many holes. So the plasmodesma and plasmodesmata are these little bits where the cytoplasm is sort of linked across two cells. So this is the cytoplasmic pathway. And again, in your textbooks now, it calls it the cytoplasmic pathway. Okay? However, from the, how we've all been taught, old school, it's actually known as the symplastic pathway. The symplastic pathway is the cytoplasmic pathway. But I like to call it the apoplastic and the symplastic pathways. Okay? You should get the marks for either one of those. Okay? Now, so what happens then? So it keeps moving in a forward direction. Well, why does it move in a forward direction? It moves in a forward direction because the cell in front must have a lower water potential than the cell behind. So if you imagine that is the outside where it was in the roots in the soil. Water moved in by osmosis because the cells inside the root hair cells had a lower water potential, which means the cell behind it had a higher water potential. So you go from high to low. But then this one has to be higher than this one. So then this one will move from high to low. But then this one must be a little bit higher than the one in front. So then this one will move from high to low. And then this one will move from, that's slightly higher than the next one, so it'll go from high to low. So it keeps doing that. So the cell in front always has a lower water potential than the cell behind. So the water will keep continually moving by osmosis from a high water potential to a lower water potential in the forward direction. And there's two paths it can take. It's like two parallel roads. I call them like Bristol Road and Pershore Road. Okay? If nobody knows what that means, if you live in Birmingham, you will. Two major roads coming into Birmingham City Centre, pretty much in parallel. Okay, going past the Edgbaston Cricket Ground now and Birmingham University. So as you come along those, you're coming towards town, two loads of roads, loads of traffic. Okay, not like today because we're all in lockdown and isolation. If you go into the streets, there should be no cars because everyone should be staying at home and staying safe and washing your hands. But these two roads are going along, and imagine suddenly one of the roads has to close down. So they shut down one of those roads. What's going to happen? You all need to get to town, all right? So you need to get to your bouldering for your Christmas shopping or whatever, right? So not right now because we're in March, coming into April, but anyhow. So if you imagine these two roads coming in together and then one road gets shut down, what's going to happen to the traffic? You can either just stop that traffic or you all need to get to town. What will happen, Pershore Road and Bristol Road have got little side roads that connect them from to one to the other. So what would happen is that if you shut one road down, all of the traffic on that road will converge onto the one road. Let's call it the Bristol Street, okay? Or Bristol Road, whatever. So they come together, so you suddenly have a huge number of cars on one road. So you massively increase the number of the traffic on one road. So the pressure massively surges. Now, why am I giving you that analogy? Because that's what happens when these two roads, the apoplastic and the symplastic pathways, once they converge. So here, we've been looking at this cross-section of the route. We're just zooming in to this bit here. We've got our two pathways. We've got apoplastic going through the cell walls. We've got the symplastic going through the cytoplasm. But once it gets into the endodermis, the endodermal layer, okay, remember the outer layer is the epidermis. This layer here in the middle is the endodermis. The water's been transporting through the apoplastic pathway and the symplastic pathway, two pathways. Suddenly, the symplastic can carry on, but suddenly the apoplastic has to diverge. Because see this little purple strip there? In the endodermis, there's a special layer called the Casparian strip. And it's an impermeable, sort of a waxy, impermeable, impenetrable barrier to water. So that water can't carry on through the apoplastic pathway. Your name's not down, you're not coming in, right? So it can't come that way, it has to diverge and go around and join on with its buddies in the symplastic pathway. Suddenly you got all this water in a small space, in a small volume. What happens to pressure? Pressure massively increases. So the pressure massively increases and it all surges into the xylem. And not only that, you've got in the xylem, right in the middle, remember right in the middle there, so you can see in the grey, that little X marks the spot, that little X there is the xylem. Suddenly you get this surge of water going into there. Not only that, you've got active transport kicking off in there, pumping minerals into that xylem right there. So therefore, if you're pumping in mineral ions into that xylem there, you've suddenly really reduced the water potential. It's gone really salty. So that means here it's really dilute. So water will move from a high water potential from here into a low water potential into the xylem, but with such surge and such force that it produces something called root pressure. And that's really important because the root pressure is the beginning of that water going up the stem, okay, going up the stem and on its journey up to the leaves at the top. So water, remember, keeps moving in a forward direction. Remember that I was talking about it has to go from high to low, high to low, high to low, high to low. Well, why is it doing that? Because this is the middle where the water potential is really low. So that means that's low, this is higher, that will go that way. That means now that is higher than this one, so it goes that way. That means this one is lower, that's higher, so it goes that way. So it's kind of a domino effect. It keeps moving forward. It has to, because the guy in front has got low water potential compared to you. You've got higher than him. The guy behind you has got higher water potential than you. So he's going to move into your space and you're going to move into that space. So that's how water keeps moving forward until it gets to the xylem and you get that little root pressure. Now, why is root pressure important? It gives a little kick, gives that little thing. But at the beginning I said, well, the hosepipe can't reach the top. No, it can't. It can't go really high. It can't go tens of meters. But what it can do is probably go about a meter-ish or so, which is pretty good because for the little plants, like little flowers and little grasses and little bushes, okay, they can live off just the root pressure. They don't need to have the transpiration pull because it's a pulling effect, not a pushing effect, okay? So, well, little tiny plants they could live off just the root pressure itself because the water can get about that high. But we know, the evidence shows that it's not a pushing effect because if it was a pushing effect, then it caused bulging because if it's pushing outwards, it cause bulging in the trunk of the tree or the stem, but it doesn't. During the day, the trunk actually narrows. And I'm going to come on to that in a second because we're going to talk about something called the cohesion tension theory. So once the water's got up about this high, the rest of the water, or the water, needs to be pulled up the stem and into the leaves. So how is it pulled up? Well, it's pulled up because in the leaves, you've got negative pressure. Where does that negative pressure come from? That negative pressure comes from the fact that water is evaporating out of the stomata. And if water is evaporating out of the stomata, that means there's less water in those cells in the leaves, in those spongy mesophyll cells, because they're sort of diffusing out of there into those air spaces and then out, thereby lowering the water potential, so the water keeps moving in a forward direction and water keeps evaporating out. And if you've got a negative pressure, you have that pulling up effect. Okay? How does that happen? How do you get this negative pressure? Well, it's a bit like sucking a drink on a straw. If you're having your drink, there are, I mentioned many, but I'm not allowed to advertise. You're drinking your flavoured sparkly drink, that's brown, cola. So you're drinking that drink with a straw. Now, how does that drink get into your mouth? Do you suck on the straw for the drink to go into your mouth? No. What's actually happening is you're removing the tiny bit of air in that straw, making it become negative pressure or zero pressure in there because you've taken out the air particles, and therefore the atmospheric pressure from the outside is pushing down on that drink and forcing the liquid through the straw and into your mouth for you to take a slurp of your chug jug or slurp juice or whatever you kids call it these days. Anyway, so now, okay, if you've all got off your cringe. Now, the water will evaporate and it'll cause that negative pressure and it will go pulled up the stem into the leaf. And this is known as the cohesion tension theory. That's the explanation we use to show the how this process happens and the theory behind it. So what do I mean by this cohesion and this tension? This is just a quick overview of the symplastic pathway of what we've just been talking about. So this is zooming into that diagram that we've just looked at previously. And this is looking at the water potential gradient, how water will move into the root hair cells, and it'll keep going down that water potential gradient. It'll always go from a high water potential to a low water potential, down that water potential gradient. So it keeps going from high to low. This one's going to be higher than that one, so it's going to keep moving forward and forward. So that's the root hair cell, the first cortex cell, the second cortex cell. It's always going to keep going that way. And right, the cohesion tension theory then. So the apoplastic pathway then is going through the cell walls. Now water, if you think about we did this back in chapter 2 I think it was, and if you do A level chemistry you'll know that water it's a bipolar molecule. Okay, you've got the oxygen molecule and you've got two hydrogen molecules, and there's electronegativity, which basically means the oxygen pulls on those, the covalent bond isn't sort of equally shared. So the oxygen pulls harder on those shared electrons than the hydrogen does. So on the oxygen side, there's a slight negative charge. And on the hydrogen side, because you've got the slight negative there, it'll be the opposite. It'll be the hydrogen charge, the positive charge. So therefore, one bit's delta negative and the other one's delta positive. You've got these hydrogen bonds. Hydrogen bonding makes water a liquid at room temperature, and that's the unique nature of water. Water is an amazing thing. It allows life to happen and occur on Earth because the temperature on Earth, the ambient temperature, is approximately 10 to 15 degrees Celsius. That is, coming on not far from room temperature, but that is the temperature where water will be a liquid. Because if you go below 0, it'll be ice. And if you go above 100, it'll be vapor, it'll be steam. And if you go to the closer planets, that's what would happen to water. And if you go to Mars and further out, it's ice. So life can't exist. Water can flow in the liquid form between 0 and 100. So therefore life can exist because all life requires water in the liquid form. As I said, it's a universal solvent and all the other things. Now, the nature of water though is because by the laws of physics, the other molecules, if you think about methane, think about oxygen, think about carbon dioxide, think about other simple covalent structures, these molecules, they're gases at room temperature. Water isn't. And water is a smaller molecule than some of them, like, for instance, carbon dioxide, which is heavier. So that should not be a liquid, but it's not. Water, H2O, hydrogen oxide is. And that's really good because these hydrogen bonds make it sticky, so water sticks together. So they come and stick together. Not sticky as in like glue, like you got super glue stuck to your fingers or something, but sticky in the sense that the particles stay together. And because of that, that's the cohesive nature of water. Water sticks together and it makes a continuous column. So these are the three phrases we need to use. Continuous column. You have a continuous column of water that is flowing through the stem. So that's the cohesion bit, the cohesion tension theory. The cohesion bit is because water has sticky nature, cohesive nature because of the hydrogen bonding. It will stick water to water, but also up the walls of the xylem. So it's sort of creeping up the walls of the xylem as well, just sticking to the walls and going up. Okay, so you've got, that is the cohesion bit. The tension bit then, the cohesion tension theory it's known as. The tension bit is the fact that, come back to that. The tension bit is the fact that water is under tension. Why? Of the negative pressure. The water is evaporating out of the leaf. The water is evaporating out of the leaf there through the stomata, because once it goes through the xylem, okay, because remember the water's been pulled up because of the transpiration pull, it's been pulled up. Once it gets into the leaf, it goes into these cells in the palisade mesophyll layer, it goes into the spongy mesophyll layer. Once it's in those cells, it will go through the apoplastic and the symplastic pathways to get to the different cells that it needs to get to. Once it gets to the spongy mesophyll, it eventually ends up as water vapor in these air spaces, and then it will evaporate from a high water potential to a low water potential through the guard cells, through the stomata, and into the atmosphere. Okay, and because of that, you get a negative pressure, that sucking up effect. Now, if you think about, if you get a paper straw, they're starting to do that now in all the establishments like McDonald's and other fast food chains. Instead of we're trying to reduce our use of plastics. Plastics tend to be more stiffer, so when you drink them, they don't tend to collapse. But if you get a paper straw and you suck on it too hard, what happens to it? It collapses, doesn't it? Because it's not very rigid. Whereas the xylem are like wooden tubes. It's like having wooden straws. And because of the negative pressure, stops them from collapsing. All right, but they are under tension because there is a sucking up effect. Now remember, some of these trees, it could be tens of meters of height, really, really high, pulling all that water, that really, really heavy water from the ground, taking them all the way to the top. Okay, how? It's just evaporating out of the top and it's pulling up on them. And if you suck on a straw hard enough, they will start to squeeze inwards. And that's why the water is under tension. It's under tension. So what evidence do we have of this? There's this, and if you look in your textbook in the sort of how science works bit, that green box, you'll see that bit about hug a tree. Now, what do we mean by hug a tree? It sounds like kind of a strange kind of eco-warrior thing to do. Hugging a tree. Are we talking about going around hugging trees and, you know, trying to be friendly with them? No, that's just strange. You just get arrested. But if you went to a tree in the middle of the day, okay, so like lunchtime, 12 o'clock, when the sun is at the highest point, and you put your hands and arms around the tree, and you could literally put your fingers around it, and your fingers just touch, okay, that would be sort of like the circumference of the diameter of the tree trunk. Now, if you went back to that tree in the middle of the night, and you did the same thing, you probably would get arrested, because that's just odd, but if you did do the same thing, your arms wouldn't get around the tree. That's strange. It's the same tree. How did the tree suddenly get fatter overnight? Too many pizzas? No. What happens is, during the night, what happens? Stomata close. Why do they close? Well, they don't need to stay open. There's no photosynthesis. If there's no photosynthesis, why stay open? Because you could be losing water. Waste of time. It's a waste of energy. It's a necessary evil. There's no point just having evil for the sake of evil. So, stomata close. If the stomata close, are you losing water? No. If you're not losing water, are you causing that negative pressure? No. If you're not causing that negative pressure, then you're not having that pull-up effect. You're not going to have the trunk being sucked inwards, okay, being narrow, like it is in the middle of the day when the sun's at the highest and photosynthesis is at its fastest, okay, you're getting the water stop coming out, and therefore the trunk starts to bulge out more because there's more water in there. That's a bit more evidence to show you the negative pressure effect of the part of the cohesion tension theory. All right, so cohesion tension theory: water sticky, sticks together. Tension, it's under negative pressure, it's been sucked up, so therefore it's going in. So that's the cross section of a leaf. All right, so just quickly a revision: you get your waxy cuticle, you get your upper epidermis, lower epidermis, you've got your spongy mesophyll, your palisade mesophyll layer there where most of the photosynthesis is happening. You got your spongy mesophyll there, and you got your lower epidermis, and you've got your guard cells, and you've got your stomata. And you can see the blue pathways are your apoplastic pathways, it's calling it the cell wall pathway, and the red ones here are your symplastic pathways, or your cytoplasmic pathway going through the cytoplasm. So in summary, before we have a quick look at some exam questions, this is sort of your root hair cells, showing you root hair cell, going through the cortex, through your symplastic and apoplastic pathways. It gets to this bit here, the endodermis, because remember this is the epidermis, the endodermis here. The symplastic can carry on, but the apoplastic can't. The blue one gets diverged there by this Casparian strip because it's waterproof. Therefore, both water goes into one pathway, and then there's root hair cell there in the middle of the xylem there, in the middle of the root, pumping lots of minerals in there by active transport. Therefore, water surges into there, causing lots of root pressure, forcing the water up. But remember, how did the water get in there in the first place? Active transport of mineral ions. Therefore, water moves from a high water potential to a low water potential because you've actively transported minerals. And keep moving in a forward direction because there's always a higher water potential behind and a lower one in front. Once I'm there in the bottom, in the stem, water gets pulled up. You've got root pressure which gets you up a little bit. And there's a little chop there to show you that this is the bottom, this is in the roots underground. Go up a few meters, keep going, and then you get to the leaves. That is a leaf that's upside down. It's just for graphics, you should have had it that way around because it's the wrong way around. But you go up the xylem, and once you're in the leaf, again you've got the apoplastic and symplastic pathways. It ends up in the air spaces, the water vapor, guard cells are open, and the water evaporates out of the stomata. And that is a summary of how transpiration occurs. So, forces responsible for moving this water then, we've got the transpiration pull, which is the negative pressure pulling it up. We've got the root pressure, okay, because it's being pushed in that way. Capillarity, what that means is the capillary effect. So it sort of creeps up the sides. So if you ever look at a little thin tube or a measuring cylinder, you can see the water level sort of creeping up the sides of the tube. Like forms that meniscus. That's sort of the capillary effect. Okay, it's trying to get pulled up. It's like a thin type of piece of glass. If you put it in water or any liquid, it creeps up that little tube. So this is sort of a quick overview. Let's have a look at some exam questions. So we've got the transpiration pull. So why the water evaporates on the leaves, creates a diffusion gradient or water pressure gradient, so water will move out. The tension exists in the water column, extending from the roots to the leaves. It's the adhesive and the cohesive forces that keep the column of water continuous, that's the cohesion bit. Thus water continues being pulled upwards and water evaporates from the leaves. So root pressure is due to the fact that water moves in by osmosis because of the active transport of mineral ions into it. And then you've got the capillarity, which is the spontaneous movement of water through the tubes, sort of creeping upwards in very short distance. So that's the overall view of transpiration. Okay, this is a sort of graphical look at it. So it goes through the roots, up the stem, into the leaves, and evaporates out. That is your transpiration. Quick exam question, have a look at this. Press pause, have a go at this exam question, and the mark scheme will come up on the next slide. So question 2A, explain how water enters a plant root from the soil and travels through to the endodermis. And question 2B, From the root, water is transported upwards through the stem. Explain how the evaporation from the leaves can cause the water to move upwards. So this is what we've been talking about. So press pause, have a go, answer the question, see how many of the marks you can get from what we've been talking about, what I've been talking about. Okay, so if you've had a go at that, here's the mark scheme. So this one was just about the roots. Well, water will move into the root hair cells by osmosis. Why? There's active transport of mineral ions. So that's another mark. There's a maximum 5 marks here. And creating a water potential gradient. The water will keep moving by osmosis towards a cell in the forward direction because the cell in front always has a higher water potential. So the one behind has a higher water potential than the one in front. And then you need to also talk about the 2 pathways. You've got the apoplastic pathway, which is through the cell walls, and the symplastic pathway, which is through the cytoplasm. There's your 5 marks. And the previous question was asking about how the water moves up the stem. The water potential in the leaf of the cells decreases because water is constantly being evaporated out. Therefore, cause a negative pressure. Water will continuously move up the xylem via osmosis, and this creates that pull, that tension in the xylem. Last question before we call it a day. So, question 1A and 2B, the other way around. Root pressure is a force that is partly responsible for the movement of water through xylem in stems. Explain how the active transport of mineral ions into xylem vessels in the roots, resulting in water entering the vessels and then being moved up the xylem tissue. So it's very similar to the previous question on 2A. And 2B, the presence of an air bubble in a xylem vessel in the stem blocks the movement of water through that vessel. Use the cohesion tension theory to explain why. And that's 4 marks. So that's basically saying you've got a bubble. So if you imagine I've got my tree and I sort of get a saw and I start cutting into the stem or into the bark, I might suddenly get a bubble, air bubble trapped in that into the xylem. What's going to happen and why? So have I got those questions? Press pause, have I got those questions? And the answers are coming up now. So the mark scheme is a 5 mark and a 4 mark question. So water potential in the xylem reduced by the entry of the ions, by active transport. The water potential gradient is established. Remember, the water can go through then by osmosis from the cells from a higher water potential to a lower water potential. So water will always move in the forward direction because there is a gradient. Now that pressure will be formed in the xylem because active transport of mineral ions into that xylem, like we said before, and that will cause a force of that water to move up. And the last question, if you cut into it and you get a bubble trapped in there, the evaporation from the leaves, you've got the transpiration, water in the xylem is under tension because of that negative pressure. And the water moves up there, it's cohesive, will stick together with the hydrogen bonds because it forms by a single column of water. But if you put an air bubble in there, you're going to break that single column of water, which means you're going to prevent the cohesion bit. If you're going to prevent the cohesion bit because the water's not stuck together, it's no longer going to get pulled up as one continuous column. Therefore, you're going to stop transpiration. The plant's going to die. Okay, it's a bit like if you imagine brakes in the movies where they're pressing the brakes and the brakes stop working because you've cut the brake pipes or something. The brake fluid leaks out. If you've got a bubble trapped in the brake pipes and you press the brakes down, nothing's going to happen. It's not a continuous column of liquid. Okay, same thing here. If you haven't got a continuous column of water because there's a bubble trapped in there, or you damaged it by cutting into it or something, then the water will no longer continuously flow up the stem into the leaves. No water in the leaves, no photosynthesis, no turgidity of the leaves, no photosynthesis, no glucose, no respiration. The plant's going to die. Okay, so hope that's been useful for you. I tried to do it very quickly. It was a long lesson. It's quite a tricky, tough lesson, and that's why I've split this transpiration lesson into 2 sections. So next time I'm going to look at the factors affecting transpiration and the use of the potometer. Now I know I've done that with you guys back in chapter 6, but I did mention that it doesn't really work that well with that chapter. I've gone through it. I'm going to revisit it tomorrow. So watch this space. Your 12s keep busy. Make sure you're using your caboodle textbook. As part of your learning, make sure you're doing those summary questions. You're doing the exam style questions at the end of the chapter, and you're making sure you're getting your notes done. this week then I'm going to finish off with the transpiration factors affecting it. Thursday's lesson will be, because you know your lessons are Tuesday, Wednesday and Thursday. Thursday's lesson will be on the translocation, which is the movement of sugar. I'm going to see if I can get those double lessons done as one, because it shouldn't take as long, I hope. If not, I'll have to possibly finish it off after Easter, if it takes over 2 lessons. And once we come back after Easter, I will be following up doing Mrs. Martin's lessons. I'll be covering biodiversity. I've already spoken to Miss Martin about it and she's really happy about that. And Bianca's also, there's a shout out for Bianca, she's also requested it via the YouTube channel. If you need to ask me any questions, you can ask me via the Show My Homework app, or you can just YouTube me through there. If this has been useful, then My Smart Learning is where it's at. And please keep watching the videos, keep liking the videos, subscribing and sharing. Take care, and I'll see you tomorrow, and I'll see you next time. Bye.